All attendees are in listen-only mode.
Hello. We are waiting a few minutes for other participants to join, and then we are going to start. Okay. Good. Let's start. First of all, welcome to this free webinar brought to you by Codemotion. This webinar is part of a series in preparation for the upcoming conference that will happen in Milan on June 14th about blockchain and crypto values. So I hope to see you all there. In the next 40 minutes, we will try to answer those two questions. Sorry. The first question is, what is stored inside a block in a blockchain and what is suitable for? And what is worth to store inside and what is better to store outside? Because we talk a lot about blockchain, but sometimes it's not very clear what is capable of storing or not inside. So first of all, let's start saying that there is no such a thing as blockchain. Blockchain is an umbrella term describing several technologies that were put together and assembled in a way in order to make them work. And from a historical point of view, of course, the first successful implementation of those technologies that we call now blockchain was Bitcoin in 2009. And today we will focus on the two most relevant open and open source implementation, Bitcoin and Ethereum. Ethereum was the second successful one in 2015. So when we talk about all those technology, we talk about three main components: cryptography, game theory, and peer-to-peer networks. So we use cryptography in order to sign all the information that we are going to store inside the blockchain. And we can use different kind of cryptography and different level of cryptography. And we use the game theory in order to set up some rules about how to build consensus about what will be the next block. And we use the peer-to-peer network in order to propagate all the information that each node preserve and so on. So depending on how you mix those three components and the underlying technologies, you may have different flavors of blockchain. Talking about Bitcoin and Ethereum, we are in the upper left quadrant. So they are permissionless and public, which means that you have not to ask anybody to be part of the network. You can join the network freely, and every node has the same rights on the network. So it's open and require no permission in order to join. You may have other different kind of blockchain flavors, but today we will focus only on those two. So what is a blockchain? Actually, it's a chain of blocks kept together by some very clever cryptographic functions in order to ensure that the blocks are chained in the right way and nobody can change these chains. And so cryptography is used to ensure that nobody can alter the content of a block after it has been mined. And blocks may have or may have not actually limited storage size. This is, of course, from Bitcoin. And the other very important thing is that blocks are chained in a sequential way. So there is a starting block, which is called the genesis block, from which a chain starts. Of course, at some point in time, there may be some diversions of this sequence of blocks, but the way that consensus is built, the game theory is used inside blockchain, ensure that at some point, usually quickly, all the inconsistencies between different kind of blocks and chain are resolved into a sequential stream of blocks. And of course, the other important thing is that in order to be public and permissionless, all the blocks should be propagated to all the peers of the network. The more the peers, the most secure and unforgeable the blockchain is. So let's take in consideration Bitcoin, the very first implementation of a successful worldwide blockchain. So what's inside a block? Inside the Bitcoin block, there is actually a bunch of transactions. And this very simple picture is very important because it tells us few key points, very important key point about how Bitcoin builds transactions. So first of all, a transaction, if you want to spend some money, if you want to pay someone some money, you have to take one previous transaction that holds Bitcoin and compose a new transaction. And this is called the input part of the new transaction. Let's say that we have a transaction A holding some Bitcoin and transaction B holding other Bitcoins, and we want to pay 0.007 Bitcoins to someone else. So given the fact that transaction A has 0.005 Bitcoin and transaction B 0.003 Bitcoin, we need to bring them together in order to have enough amount of money. Actually, we see that we have more money than the money that we want to transfer. So we have 0.008 and want to transfer only 0.007. But you have to keep in mind that the difference, the balance between input and outputs determines also the fee that is going to be paid to the miner. So actually, when a miner mines a block, it receives two rewards. One reward for the moment, until all the Bitcoin are exhausted, is in form of Bitcoin. So the very first transaction will be a reward for the simply a reward for the miner. But all the other transactions present in the blocks will compose the actual fee paid to the miner in order to repay his efforts in terms of electricity and computing power. And this is automatic. You don't have to explicitly say how much you want to pay. So you have to pay really a lot of attention on the balance of the transaction, because all the difference between your input and your outputs will be paid automatically to the miner. This is how the miner is incentivized to mine, to spend money and energy and computer power. Okay, so let's go to a deeper detail. Of course, you can explore the blocks through a bunch of block explorer, and we will go to do it soon. And from a website like this, you can gather basic information about the blocks. I think this is the information regarding a single block. and or about transactions contained in the block. Here we can see that inside this block, the very first transaction is a special one with no input, which is called the coin base. So each block has at least one transaction inside the very first, which has no input and has only output for the miner who has mined it. So in this case, we pay 12.95 and something Bitcoin to the miner. And then after we have a normal transaction made of one input of 10 Bitcoins and two outputs. Of course, as you can see, one of the two outputs is the same address as the input. Why? Because if you want to pay less money to someone else, you have to keep in mind that if you don't make your change against your address, you will lose this change. It will flow into the miner fee, as you can see downstairs. Okay, but this is a very high level representation. Okay, so if we want to go deeper and see actually what the block is, it's better to install something else. For example, you can install on your computer the Bitcoin core implementation, which is the reference implementation in the Bitcoin world. Here you can compile and you can use these very basic commands in order to extract information. So let's say that we want to see what's actually inside a block. First of all, we will take a look at the very first block of the Bitcoin blockchain. So this is the Genesis block. As you can see, is a block made only of just one transaction and exactly of just one coin-based transaction. So let's say that we want to see what is actually look like. So here I have no terminal because you need to use it's a bit more complex to have an online system here. I don't have enough resources on this laptop. So this is the actual output of my terminal. So first of all, we issue through the Bitcoin command line interface. We can do also programmatically these kind of things. We ask for the block of 8.1. So blocks are ordered starting from 1 in Bitcoin, from the very first block, and we get back an hash. This hash is the fingerprint of the block. So we can refer to the block by 8 or by hash. Once we got the hash, we can ask for the real content. And what we got in a human readable format is the actual content of the block. Okay. What is important to understand is that in Bitcoin, blocks, okay, and transactions are in a very are encoded in a very defined way. So, for example, this is the specification for the block header, the one that we are looking here. So when we look at the block, we look at a stream of bytes, usually represented in hexadecimal format, but we can interpret the content of the header following the specification. So there is a version indicating which kind of version of the block we are looking at. Of course, there is a previous block, a pointer, an hash pointer, signed in cryptographically in order to ensure the chain. There is another fingerprint, which is the Merkle root, which is the fingerprint of the transactions contained inside the block. As you can see, every hash is very small. It's just 32 bytes long. And that's a key point in all this kind of implementation. Then there is a timestamp indicating when the block has been mined, has been created. And then there are other information, the bits and the nonce, which are referring to the game theory target difficulty of mining this block. And at the end, we have the transaction count. So This same information is visible here, okay? So, which is the actual information encoded inside the block binary representation. So, as you can see, inside the block, there is also an array of transactions. So, if we take this, which this is the hash of the transaction, and this is the signature of the list of the transaction, the Merkle root. So in this case, we have just one element, so the Merkle root is the same. But again, if we look at another more complex example, we can see the difference. The key important point here is that the Merkle root ensures that we can verify the content of the transaction list, and that the hash, the transaction, can be verified against the content of the transaction itself. So the hash is very representative of the content. And given the hash representing the content, we can ask Bitcoin client to get the transaction raw content. So this is the actual content in hexadecimal format of the transaction. And we can also see how long it is. In this case, it's 268 characters long. But of course, this is not very practical to read. Again, also the transaction has an header and then a more complex structure. So the transaction basically is the implementation of the picture we saw at the start. So you have a bunch of inputs, you have a bunch of outputs, and you have other information regarding the cryptography, the cryptographic signature of both. We don't have time to go in deeper detail, but again, we can see, for example, and we will focus on the real content of each input and each output. So the transaction header is just a container, like the block header is a container of transaction. The transaction header is the container of all the inputs and the outputs. Let's go back. So once we ask the Bitcoin client to decode the raw transaction, passing it the binary encoding of the transaction, we get back this structure, which is actually the same structure that we see in the specification and also in the web browser. So this is a very special transaction. This is the first transaction, the only transaction in the very first Bitcoin block. So it's a coin-based sequence, so there is no input actually, and there is only one output. Here we have to take a look at the script pub key. So we will see the same thing also in the input in the following examples. The point is that you have to sign the transaction saying, okay, I'm the owner of this money, and I allow this money to be transferred to this output address. But you have also to sign the output in a way that only the receiver can unlock it. So this is called the script pub key, which is a script in a language, which is the internal scripting language of Bitcoin, which is not Turing complete from a technical point of view. It means that you can predict exactly how long is the script and how it will take to compute the script itself. Of course, the very basic script is just the unlocking of the value based on a private key of the receiver. So it's very simple. What you see here, the op check sig is actually an operator in the language. So this is the value you are passing to the operator, and this is the operator you apply to the value. Is almost similar to Fortran, is a very peculiar language, but it's very compact and so on. And compactness is very important in Bitcoin. We will see later why. Because the miners can't build blocks larger than 1 megabyte. So since one of the very important stream of revenues for a block, aside from the Coinbase, is the total amount of fees they can collect from transaction. So miners are incentivized to choose the most relevant transaction from this point of view. So, and the more money they can get from the fees applied to transaction, the more compact are the transaction themselves, the more they can stuff inside the block. So that's why in Bitcoin is quite unusual to have very long unlocking scripts, but we can have more sophisticated ones as well. So if we want to go deeper inside a transaction, we can actually repeat the same operation. So get a new raw transaction and the code no transaction of a typical payment. So this is actually taken from a very important book, which is called Mastering Bitcoin. The second edition in this case is an example encoded inside of the blockchain. So I strongly advise you to read this book because it's very well written. And in this case, we have finally an input. So this is not the first transaction in the block. The use case is Alice that wants to buy a cup of coffee from the Bob's Cafe. So Bob's Cafe is the receiver and Alice is the sender. So we have in this case one input. Okay. Again, we have also a script saying that, okay, this input has been signed by Alice, thanks to her private key, and she signed all the transactions, all the inputs, all the outputs inside this transaction. This is the all key you see here. And then we have two outputs. One is for Bob, and the other is the change going back to the wallet of Alice. So as you can see from the very first block in blockchain, the normal way of expressing and unlocking script based on private key nowadays is done in this way. So using a bunch of operators. But again, we can see that, for example, in this case, the actual size of a transaction is a bit larger than the first one we saw, almost twice as long. So the first transaction, the very first transaction was a special transaction, just 256 characters long, and this is almost double. So again, the more complex is the script. For example, you can have multi-signature script, so allowing people to sign for transaction in order to, for example, if you have at least 2 out of 3 signing for a transaction, making it valid, so it's quite long script. And of course, you can have more complex script as well. When inside blockchain browser, web browser, you see an output script that is not passable, it's because there is a more complex script than this one. Okay, so the other key point is that aside from Coinbase, all the inputs must be linked to a previous output, and that's why you have also this information. Okay, before going to Ethereum, we'll see just one last thing about Bitcoin, and it's colored coin. So before all this token mania exploded last year in Ethereum, and of course Ethereum is the reason why we have a lot of tokens nowadays, and that's a good thing. Also, there was also a basic implementation of what was called colored coins. For example, open asset, which is not so used anymore, but just to give an idea. So what else you can store inside a block, inside the transaction in the Bitcoin blockchain? With some tricks, you can store some information as well. Of course, again, you are enlarging the dimension of the transaction, so you have to give the right balance between input and output, and also in a way to incentivize the miner to choose your transaction. Otherwise, your transaction will remain in the cache of the pending transaction for a very long time. So in this case, the trick is to create a transaction with three outputs. One output, which is valued 0, which has no value. Use this special operator, which is op return, that is interpreted by the engine inside Bitcoin in order not to evaluate nothing. Okay, so the actual bytes following the op return may encode some information. In this case, in the open assets format, they encoded the very 4-byte was the OA prefix identifying the open asset token, and the following part was an URL pointing to some other site. So in this way, if you build a wallet capable of understanding the format you are encoding inside this, you're capable of doing covered coin Bitcoins. Of course, there are several constraints in Bitcoin in order to store very large information inside this, and we have to say that tokens really started with Ethereum. So it's time to go back to Ethereum. So Ethereum is a blockchain, but was developed with a different kind of mindset and scope. First of all, the content of the block is not simply a transaction, but is a state transition function. So the idea behind Ethereum is that Ethereum is a global, worldwide singleton, which means that you can imagine Ethereum like a big virtual machine, which a state, and each transaction is actually a function that enables the state to change from state 0 to state n. So it's not only about sending money to addresses. It's also about calling functions, retrieving output from those functions, storing a new kind of state given the execution after the execution of the function. So it's a bit more complex structure. So, and in this sense, it's encoded in a different way. Okay, of course, you can use Etherscan to get a glance of what's inside a block or a transaction. We will be there in a minute. And you can install Ethereum in several ways. This is a way of installing Ethereum with a Go implementation for command line operations. But the very first point is that as Bitcoin was built with very simple structure, the structures inside the block in Ethereum are quite complex, and they required a new way of encoding them. So they end up with this RLP, which is a way of encoding values, as you can see, single bytes, strings of some size or bigger, and lists. In this way, the decoding of the transition state and the block is quite complex and more complex than in Bitcoin, because we have to store more information. So let's take a look at what's inside a block header in Ethereum. So there are, of course, almost the same information that are in Bitcoin, plus some very specific ones. The hashing function, the cryptographic function is different. In Bitcoin, you have an SHA-2 derived function. Here in Ethereum, you have an SHA-3 derived function. But at the end, all of them allows you to build a hash, representing a signature, representing a block, for example, like in parent hash, or again a tree of transactions, like in transaction root. Here we have aside from transaction, we have these receipts root. We will go there in a minute. And the very important thing is about the gas. So, like in Bitcoin network, the currency is called Bitcoin or BTC, and is a way of incentivizing miners to do their job. Also in Ethereum, you have currency which is called the Ether or ETH. And of course, an Ether is issued every time you mine a block. But since the engine, the virtual machine, is capable of running Turing complete functions, which means that you can run loops, you have very complex if conditions. You can't predict in advance how long it would take to compute a function. So you have to introduce some limits. And Ethereum has introduced another kind of currency, which is called gas. And it's used to say, okay, I want to run this function, and I want to spend at max this amount of money expressed in gas units. And if the function is taking longer than the allowed amount of gas, please terminate it. So it's a sort of pay as you go or run as you go. So the more complex is your function, the more content you want to store inside what is called a contract, the more you have to pay for execution. And if you don't have enough gas, your function will never be executed. Or if you ask for free execution, your transaction will remain in the cache for a very long time, and eventually at some point will be probably computed, but you don't know when. So again, we have a block here, header, that is a very compact way of representing all the content inside Ethereum block. And for example, if you want to explore the gas and how much it costs to execute the function, you can use, for example, Ethereum gas station website, which is very interesting, and you can see how it's going to cost probably your function. The very first unit of execution, I mean, the minimum amount of gas you have to spend is 21 thousandths of gas unit. And of course, there is a rate of exchange between gas and Ether. It's quite complex computation. We don't have time to go in deeper details, but keep in mind that you have to pay as you go. So the Ethereum transaction is similar to a Bitcoin transaction in the sense that it collects information about two kinds of transaction. You can have a contract creation transaction. So you want to store your function inside the Ethereum virtual machine, global virtual machine, in order to execute it later in time or repeatedly. So this kind of transaction has the common fields plus a new field which contains the actual code of your function. A very important field is the nonce, which has a different meaning in respect of nonce seen from game theory in the block header, because the nonce is a sequence identifying all the transaction belonging to an address, and it's used to actually execute all the transaction in a sequence. So, for example, if you generate from an address a transaction of nonce 1 and then 2 and 3, and they arrive in different order to the miners, the miner, for example, the miner is going to receive 2 before 1, will mine 2 just after it has received or it has been mined also the 1. So it's a very sensitive information. And of course, you can have also another kind of transaction, which is a message call transaction. So you have stored your contract, you want now to execute your contract. And so you have to issue a new transaction with this field, data field valued with the name, let's say the name of the function you want to call inside the contract, and eventually some data you want to pass to the function as well. The last information inside the transaction is what is called the transaction receipt, or logs, or events. So each time a function is invoked, the function can store some output, for example, return value, or some kind of logs inside this other structure, which is called the transaction receipt. And just to be clear, you have to pay for storing the contract. You have to pay for executing the message, some kind of gas, and you have to pay also to store the transaction receipt. The price is different, so it's cheaper to store information inside logs than inside transaction, because actually it's only the real transaction, not the logs, that are stored inside the block. And the contract can also only access the information stored inside the blocks, not the logs. But you can use the logs for retrieving information from an application point of view. So everything you store inside the Ethereum block has a different kind of cost. This approach is, of course, due to the fact that you are executing functions, not simply storing balances between input and outputs like in Bitcoin. So the message is that you can store much more richer information as long as you have enough gas. Before going to stats, let's take a look at the very first Ethereum block. This is the Genesis block of Ethereum. What we see here are the same information that we see on the specific reference. We can see that inside this block there are a lot of transactions. Actually, this is different between the Ethereum Genesis block and the Bitcoin Genesis block. And if we can go inside one of these transactions. But what I want you to show, and of course, due to the fact that it's quite complex a structure, it's more easy to display it using a web interface or a more complex interface. So just to finish this part about Ethereum and approaching the end also this webinar, we can see here the logs. So for each transaction, you are looking at the transaction of a specific contract. So this is a contract. These are all the transactions belonging to this contract. So all the calls that has been, all the function that generated by each call. And as you can see in the specification, for each transaction log, you have actually an array of logs identified by a topic. So you can have multiple topics. And for each topic, you have an array of data. Of course, we don't know how to interpret this data in the sense that it's the contract that knows what it's going to store inside the logs. And of course, the application that wants to interact with the contracts need to understand which is the behavior of the contract. For example, we can see the code. These are the function in Solidity language, which is a far bit more complex language than the language used inside Bitcoin. And this is a reference of the functions that can be called by the external applications. So an application calling one of these functions will have to retrieve or could retrieve the output inside the logs and apply the required pattern to understand, for example, if this is a text, probably not, or is a number, probably yes, we don't know, or an address, we don't know. Okay, we have to go deeper inside the code and the contracts and the contract in order to understand how to interpret this log. But as you can see, in Ethereum, you can store very more complex things than in Bitcoin. Of course, now we have to understand, is it possible to say that one is better than the other? It depends. So if you look at stats, for example, we can see, you can see in the graph on the left side of the screen, that, for example, that the size of the blockchain is growing faster for Ethereum than from Bitcoin. Bitcoin is the blue line and Ethereum is the red line. Bitcoin is around 250 something gigabytes of disk used at the moment, and it is growing towards 1 terabyte, something more as of May. So depending on how many transactions you want to store, how many things you want to store inside the block, the complete size of the blockchain can grow at very expensive rate. So why I'm saying this? Because we said at the starting of this webinar that we are addressing a very specific kind of blockchain in this talk. So the permissionless and open blockchain, which means that you have to allow people to run nodes in a sustainable way. So I'm not talking about mining in this case. Mining is a completely kind of different thing. We are talking of the resource necessary in order to just run a node and store all the blockchain. So why you want to store a blockchain inside your computer? Because you want to have control on the validation phases. You want to trust a verified blockchain and not trust someone else. So in order to depend on some risky external authority. And on the left, you can see the size of the block. So you can see that if blockchain, Bitcoin is almost 1 megabyte nowadays, and Ethereum has very smaller blocks. And this allows Ethereum to have a much higher rate of transactions. As you can see, almost 3 times more than Bitcoin. So the balance of all those things, how big should be the nodes of your blockchain network? How big is the block and how fast or slow it propagates through the peers? And how many transactions are you capable of doing inside your network? Determines the kind of flavor and possibility of the blockchain you are offering or you are using. That's a very important thing. So I would like to finish saying that, okay, so you want to use a blockchain. And for me, these are the questions you have to pose, and you have to find an answer for them in order to see if the blockchain you are going to use is the right one for you. So the first question is, who can set or change the rules of the protocol and establish which is the next real next block? And who runs the nodes and pay for them, because nodes are required not only for mining but also for validation. So if they are very expensive, who are going to pay for them and how? And of course, who validates the blocks and at which cost? And the last but the more important, given this talk, is who can read, but more important, even more important, who can write on the blocks of your blockchain. And this is all. Thank you very much. And I think that we have a few time for a question. I suggest you to read this article from Wired, which very appears a few days ago, about all the things that at the moment people say that blockchain is supposed to fix, and most of them probably are not. So it's time for questions. Thank you very much. You can send your question through the GoToWebinar. Any questions, any doubt, any curiosity? Okay, so we have a question from Lorenzo Cianciaruso. What's the mechanism to access the blockchain network if there is no central entity? Is peer-to-peer technology. So it means that when you fire up your node, what happens is that the nodes search for broadcast a request to the network, and see if there are other nodes available, and establish a connection to a bunch of those nodes. So the number of connections, number of peers is almost limited, in the sense it's always limited. You don't connect to all the peers of the peer-to-peer network, but just to a bunch, and you establish with them a relationship and a contract that says that every time that one of the node connected receive a new block from a miner, it should propagate the block to the other ones. Or if you are a miner and you are connected to other peers, once you have a valid and validated block, you have to propagate the block to the other peers. In this way, the topology of the network is always changing, because nodes may appear and disappear, but it's basic peer-to-peer technology. I hope to answer this question. So what about of course, the question I think is from Luca Grande is, what about more Bitcoin by routing payments? So of course, there is a huge debate about the fact that Bitcoin has a very slow transaction per second capability. This was by design. I think Satoshi Sakamoto was right about this. So in Bitcoin, you have a new block every 10 minutes, and each block can't be more than 1 megabyte inside. So you can pack inside the block, and you can process in a specific amount of time a very limited number of transactions. So nowadays, there is a very interesting technology which is called Lightning Networks, on top of Bitcoin and probably on soon other blockchains, that allow to establish trusted channels between nodes and route in a very clever way through those nodes a payment request. The idea is that you use the blockchain for the most valuable part of the microtransaction. So, for example, let's say that you always take coffee from a specific cafeteria, and you want to pay this cafeteria with Bitcoin. Instead of asking the Bitcoin network to store every micropayment, you just ask the Bitcoin network to say, okay, I want to pre-allocate an amount of money, like you do in a prepaid card. And through a very complex, we don't have time to explain it, but through a very complex way of dealing a contract between you and the cafeteria, you can start consuming this amount of money between you and the cafeteria in a safe way, and then store only the balance at some point. So in this way, you have very low transaction requirement inside the Bitcoin network, and you have very high transactions inside, in a more simplified way, inside the Lightning Network. So I'm a big fan of Lightning Networks, as you can see. And the other important things about Lightning Networks is that the routing, so let's say that I want to pay something to a specific cafeteria, but I'm not connected. My node is not connected to the cafeteria, it's connected to a friend of mine. And this friend of mine is connected to another friend, and so on. And after 10 friends, actually one of them is connected to the cafeteria. The Lightning Network allows you to say, I want to pay the cafeteria, passing through all your chain of friends, with a high level of security and anonymity. So it's very interesting. I think that's the future. Okay, I think I've responded also to Luca Grande. Any other question? Okay, let's see. Anyone? Okay, I think that we can finish this webinar. Thank you all for your participation, and I hope to see you all at the conference in Milan. Bye.